Today we explore how Rudolf Clausius discovered one of physics' most profound principles through careful analysis of heat engines. Clausius studied heat engines, machines that convert thermal energy into mechanical work, and discovered something surprising about their fundamental nature. Let's begin with the ideal reversible engine that Sadi Carnot proposed in 1824. Carnot proposed a theoretical heat engine that operates in a perfectly reversible cycle between two temperature reservoirs. The engine absorbs heat QH from a hot reservoir, produces work W, and rejects heat QC to a cold reservoir. Carnot showed that the maximum efficiency depends only on the temperature ratio, given by 1 minus T cold divided by T hot. For this ideal reversible cycle, Carnot discovered a special mathematical relationship between heat flows and temperatures. The heat absorbed, divided by the hot temperature, equals the heat rejected, divided by the cold temperature. This perfect balance defines reversibility. In the 1850s, Rudolf Clausius began examining real heat engines and discovered they behave differently. Clausius measured real steam engines and found they always produced less work than the Carnot ideal predicted. Real engines required more heat input, but produced less work output. The losses appeared as waste heat and friction. Clausius asked, if energy is conserved, where does this lost work capacity go? The answer: it dissipates as low-grade heat that cannot be fully recovered. The energy exists but becomes less useful. Clausius performed a mathematical analysis that revealed the fundamental difference between ideal and real processes. For any complete thermodynamic cycle, Clausius carefully tracked all heat transfers and their associated temperatures. For an ideal reversible cycle, the cyclic integral of dq over T equals exactly 0. Heat ratios balance perfectly. But for any real irreversible process, this integral is always less than 0. The heat ratios never quite balance. This graph shows the fundamental difference. Reversible processes hover at 0, but real processes always fall below, showing persistent inequality. Let's work through a concrete numerical example to see this inequality in action. Imagine a simple heat engine operating between a hot reservoir at 600 Kelvin and a cold reservoir at 300 Kelvin. Hot temperature 600 Kelvin, cold temperature 300 Kelvin. Suppose the engine absorbs 1,000 joules from the hot reservoir and rejects 600 joules to the cold reservoir. For an ideal reversible Carnot engine between these temperatures, the heat ratio difference would equal 0, meaning QC should be 500 joules. The ideal engine would reject only 500 joules, but our real engine rejects 600 joules, which is more than the ideal case. Calculating the ratio difference, 1.67 minus 2.00 equals negative 0.33. This negative value proves irreversibility. This negative 0.33 is not just a measurement error. It quantifies the fundamental irreversibility of the real process. This persistent inequality led Clausius to define a revolutionary new property he called entropy. In 1865, Clausius defined a new state function to capture this irreversibility mathematically. Entropy change ds equals the reversible heat transfer divided by absolute temperature. For any complete cycle, the total entropy change of the universe is always greater than or equal to 0. Equality holds only for reversible processes. Entropy naturally increases over time. Ordered states evolve toward disordered states. This one-way direction defines the arrow of time. Clausius's work explained why perfect reversibility is impossible in nature. Can we ever completely reverse a real thermodynamic process, returning everything to its exact initial state? No. While we can reverse some aspects, the total entropy of the universe always increases during real processes. Time flows in one direction because entropy grows. We cannot unmix coffee and cream or unburn fuel because entropy forbids it. Real processes involve friction, turbulence, mixing, and heat transfer across temperature differences. All these create entropy. Each tiny irreversible event, no matter how small, contributes to the universal entropy increase. What does entropy actually represent at the molecular level? Entropy quantifies the number of microscopic molecular arrangements consistent with the system's macroscopic state. Boltzmann later showed entropy equals Kb times the natural logarithm of W, the number of microstates. Ordered arrangements have low entropy because few microstates look organized. Disordered arrangements have high entropy because many microstates look random. Higher entropy corresponds to more molecular disorder, and nature spontaneously evolves toward more probable high-entropy states. Clausius's inequality directly gives us the second law of thermodynamics. The second law states that the entropy of the universe never decreases. It either increases or remains constant. For ideal reversible processes, total entropy remains constant. The system and surroundings exchange entropy but don't create it. For all real irreversible processes, total entropy increases. New entropy is continuously generated. This graph shows entropy versus time. In any isolated system, entropy climbs steadily upward as irreversible processes occur. Clausius's discovery has profound practical implications for engineering and technology. No heat engine can convert thermal energy to work with perfect efficiency. Some energy must always be rejected as waste heat. Real engine efficiency is always less than the Carnot limit, which itself is less than 100% unless the cold reservoir is absolute zero. Refrigerators cannot spontaneously move heat from cold to hot. They require work input because that violates entropy increase. A refrigerator pumps heat upward against the temperature gradient, but this requires external work to avoid violating the second law. High-quality energy like electricity gradually degrades into low-quality waste heat. This degradation is irreversible. Today we understand Clausius's work connects thermodynamics, information theory, and statistical mechanics. Modern physics connects thermodynamic entropy to information entropy. Losing information about microstates increases thermodynamic entropy. Information entropy equals negative Kb times the sum over all states of probability times its natural logarithm. Even quantum systems obey thermodynamic entropy limits. Quantum computers face fundamental entropy barriers. The second law is truly universal. It governs chemistry, biology, cosmology, information processing, and even the fate of the universe. Even black holes have entropy, proportional to their surface area. This connects gravity to thermodynamics in deep ways. Let's summarize Clausius's revolutionary insights about irreversibility. Clausius carefully compared ideal Carnot cycles with real engine measurements and found systematic deviations. The heat flow ratios in real engines never balanced exactly like they did in ideal reversible cycles. This fundamental inequality, the cyclic integral of dq over t, is less than or equal to 0, captures all irreversibility. From this simple inequality, Clausius defined entropy and established that real processes are fundamentally irreversible. The second law emerged. Entropy of isolated systems always increases, defining time's arrow and limiting efficiency. Clausius's discovery governs everything from engines to evolution, from chemistry to cosmology. It is one of nature's deepest laws.